We'll resume in a second or two the discussion from Monday of vortex filaments in 3 dimensions. And so let's see. Okay, so it seems to be 5 past, and I'll go to here. And so on Monday we had started discussing the general vortex filaments in 3 dimensions. And so we started with this formal discussions. And so the point is we have a curve. We think of that as being the, we first imagine we have a vorticity of sort of delta functions of vorticity concentrated on a curve. This would be the 3D analog point vortex. We know that that's, for that thing, the associated velocity field is not an L2. So we regularize it. We smooth the curve. And then we get a, we smooth by mollifying with an approximate identity who we assume is rotationally symmetric and supported in ball rates epsilon. And we can, if we like, we can really think of epsilon as being the scale. It's not concentrated on a smaller scale. So it's like 1 over epsilon squared times eta of x over epsilon, where eta is supported in ball rates 1. Okay, we do that. And then we want to ask, we want to understand the instantaneous velocity of this epsilon vortex tube. And so we reason by saying, well, we know that the vorticity is transported and stretched by the flow. And so we know in particular that the boundary of the tube will continue to contain the vorticity at later times. And so if we can compute the velocity on the boundary of this tube, that will tell us how the whole tube is moving. Okay, so we choose a point, a distance epsilon from the tube. And so it's away from the support of the vorticity, just on the, if you like, on the boundary of the support of the vorticity, and we want to compute the velocity there. That's what we were doing. And so we started with this prototype, the epsilon equals 0. Vorticity, we have a formula for the velocity, u sub gamma. Here it is. And so we regularize it as this. And then the epsilon regularized velocity will look like this. And to understand the tube motion, we only need to understand the motion of the tube boundary. And apologies for the awful handwriting. Okay, so let's continue. So let's consider. So remember, gamma is the. So we'll consider a point x such that the distance of x to the curve gamma is epsilon, which we think was being much less than 1. And so let's say gamma of s naught. And so I'm thinking of gamma as being a smooth curve, injective, and so so for any close enough point, there's a unique, for any point, if epsilon is small enough, then there'll be a unique point on the curve who's closest to x. Gamma is not as the unique closest point to x on gamma, where the uniqueness again falls from the smallness of epsilon. And let's assume for convenience by just changing variables, I can assume that this s naught is 0. Okay, and I want to estimate u epsilon at okay, and where u epsilon is the Biot-Serrard kernel applied to omega epsilon. Okay, and good. And I think I put a omega, what was it called? Omega epsilon gamma with an arrow on top. Okay, and so there's a trick which I think we mentioned this a month or two ago. So, And so here's the trick. So by definition, recall and maybe I'm going to start omitting subscripts. U epsilon is this convolution with omega epsilon gamma. And omega epsilon gamma was itself obtained by taking this modifier eta epsilon and convolving with the measure omega sub gamma. Okay, and then we remember that convolution is commutative. And so this is eta epsilon convolve with the BSR kernel applied to omega gamma. And that's just, maybe there's a gamma here. Anyway, so that's just eta epsilon convolve with. And this here is the velocity field generated by omega gamma. I think we called it U gamma. And we may have written it up here someplace. This U gamma is here. So we have an explicit formula for that. And this is stuff we said a while ago, but remember that, well, so the BSR kernel is harmonic. It's singular at the origin, but it's harmonic. So it's a function of, so K of X is a matrix value function, and every entry is harmonic away from X equals 0. And so what this implies is that when I convolve with something, if I convolve with say something supported on the curve gamma, then away from the curve gamma, then the resulting object will again be harmonic. It'll satisfy the Laplace equation. Laplacian of this thing is equal to 0. So recall that. So in other words, so recall from some months ago that the Laplacian of U gamma is 0 away from gamma. And recall also that if I take a radiosymmetric average of a harmonic function, well, then I'll just get the value of the harmonic function to the center, because by this famous mean value property of harmonic functions. And eta epsilon of x minus y U gamma of y. Well, let's put it this way, I can write the convolution integral in different ways. Was there a noise coming from here? No. This is true if U gamma is harmonic in the support of eta epsilon, which is the set of all the ball radius epsilon. And so the conclusion is that, as we said before, that this U epsilon of x is equal to U of x if the distance of x to gamma is bigger than epsilon. So if the distance of x to gamma is bigger than epsilon, then when I do this integral, this U epsilon of then when y is in the support of gamma, then I'm looking at points x minus y who are bounded away from gamma. And this holds. Okay, and so the point is that if I'm regularizing on an epsilon scale, then the distance is greater than epsilon. The regularized velocity field is exactly the same as the unregularized velocity field. And this means I have an explicit formula for it. I can just use that formula. And so so the thing we're trying to compute is so we have a formula for it. So we said, okay, so fix x such that the distance of x to gamma is the same as x minus gamma of 0 is some small number epsilon. And so we want to estimate so U epsilon at x is just this formula we had from before, exactly the Biot-Savart kernel applied to the curve. 1 over x minus little gamma of s, the parameterization, divided by x minus gamma of s cubed, the cross product, with gamma prime of s ds. Okay, and so let's say here's a picture. Let's say x is gamma of 0 plus y. So here's the picture. Here's the curve. Here's the point x. It's orthogonal. So gamma of 0 is the closest point. That means that the vector connecting x to gamma of 0 is orthogonal to the curve. I call that vector y. So y is a vector of length epsilon, and y is orthogonal to the tangent here. I should have said before, I always assume that I have an arc length parameterization of the curve. So the magnitude of gamma sub s, the Euclidean norm, is always equal to 1. Okay, and so then I want to just do a Taylor expansions. So so gamma is gamma of 0 plus s. That's right, gamma prime. So here I'm imagining time is frozen, and so there's only one variable s. So I can write prime without ambiguity. And gamma sub s is this. Okay, let's look at these Euclidean norms. And so I want to just replace all these things by their Taylor expansions. And so, for example, well, I'll come back in a second and do this. But let's look at this. So x minus gamma of s is x minus gamma of 0 plus gamma of 0 minus gamma of s. We call this vector y, and then we'll just do an expansion here. Minus s gamma prime of 0 plus O of s squared. Okay, and that's y minus s gamma prime of 0 plus O of s squared. Okay, right? And then if I look, and so if I look at the Euclidean norm of this y minus s gamma prime of 0, well, these vectors are orthogonal. So if I square both sides, I get a y squared. I'll get a dot product, which is 0 by assumption, and then I'll get a gamma prime squared. And so this is, and y squared is epsilon squared, and gamma has norm 1. So this is an equality. And that's 1/2. Okay, so then let's go back up here and replace these things. So this is what we just computed. This is s gamma sub s of 0 plus s squared over 2 gamma, okay, double prime. Right, plus gamma prime of 0 plus s gamma double prime of 0. And then this is epsilon squared plus s squared to the 3 halves, I believe. Okay, and so imagine taking the cross products. And what'll I get? So the first term is, I've forgotten something. So there's a y. So there's an x minus gamma of 0. I did this totally wrong. If you see grievous blunders, feel free to speak up. So we had this correctly down here. This is y minus s gamma prime of 0 plus and then I'm sort of omitting the higher order terms. Okay, and so then if I look at this, the leading term will be the y cross gamma prime. Those are orthogonal, and so their cross product will be big. It'll be the same size as y. And then there'll be a gamma prime cross gamma prime. That's small. There'll be a y cross gamma double prime. That could be non-zero. These are two normal vectors. They don't have to be the same. But if you look at the associated integrator, that's going to be odd. So there's an s there. When you, so okay, here's what I'll do. So the integral u epsilon of x is, okay, so here's the first thing I'll do. So I'll integrate over some, so here's the picture. I have this curve. I'm looking at a point here. I want to integrate over a section of the curve near the point in question. And then I want to ignore it. So I'm doing Taylor approximations. I want to stay nearby. And so I'll, so I'll integrate over an interval of length tau, say 2 tau. And then I'll hope that everything else can be ignored. And why is that true? So if s is bigger than tau, then this x minus gamma of s should be also of order tau. And so this whole thing will be of order tau to the minus 2 if I'm a distance tau away from here. And so, well, okay, I'm just going to do this. Tau less than s less than L over 2, and this is like O of tau to the minus 2 ds. Okay, that's gonna be small. That'll be a small. So what I want is I want tau to be roughly 1 or close to 1, but small. Okay, and then here I can do a Taylor expansion in the first integral, and then what I can do is I can also so we'll have a y cross gamma prime of 0, and I believe that's integrated over epsilon squared plus s squared to the 3 halves. So I'm basically not being very careful with error terms. One could do this more carefully. And then there'll be so that's the term involving this the leading term. The next term is so that involves this and this. The next term would involve this and that. That's 0. The next term might involve say y and this. That's odd with respect to s, and I'm integrating over from s over symmetrically around the origin. So that won't contribute. And so then the next term is I'll get a s squared over 2 gamma prime 0 cross gamma double prime 0. And then plus minus tau gamma prime of 0 cross gamma double prime of 0 times s squared over 2. And then I have the same denominator, epsilon squared plus s squared to the 1/2. And I feel like that factor of 2 is wrong. That is That's right, so it's just s squared. Okay, and so this is going to equal, let's see, so the first term is going to be something like, so it's y cross gamma prime of 0. And then I believe this gives an integral of order epsilon to the -2. So there's some constant over epsilon squared. And so this looks like, it looks like epsilon to the -3 for distances when s is bigger than epsilon. It looks like s to the -3 when s is bigger than epsilon, and then it's sort of cut off when s is less than epsilon. So that's what we get. And similarly, the other one is going to be plus gamma prime cross gamma double prime of 0. And then there's some constant times log 1 over epsilon. And then there's more stuff. And so here there'll be error terms involving tau. And so, but we can take, so this is all negligible. So the error terms are lower order. If tau is like, say, small, so the Taylor approximation can be justified, but not too small. And so like, you know, log epsilon to the -1. Okay, and then so we look at this. And so we say the velocity then to leading order. Well, the biggest component is this, but that's purely rotational. And so remember, the y is the so I'm at a point. So this is the purely rotational as usual. So purely rotational. Gamma prime is the tangent. I'm at a point whose this vector y is the point connecting the curve to the point I'm interested in. And so gamma prime cross y is going to be rotating around the curve infinitesimally. And so we always imagine as we prove this in the 2D case that this doesn't affect the motion of the vortex fellow. And so we then look at the next term, and the next term is this, and it's of order log 1 over epsilon, so it's logarithmic. I think the constant is going to be 4 pi if we were careful, or 1 over 4 pi, I believe. And then this gamma prime 0 cross gamma double prime 0 gives us the velocity vector, the direction and the magnitude of the motion up to this rescaling logarithmic factor. So let me remind you, or recall when we looked at vortex, we saw again this logarithmic scaling factor. This is the same factor there. And so I claim that this is the, so what does this mean? So anyway, so this suggests that the velocity of the tube, and so the point is that no matter where I am on the boundary of the tube, this next term is always pointing the same direction. So this gamma prime cross gamma double prime doesn't depend on the direction of the vector y. And the velocity of the tube should be gamma s cross gamma s s. So the conjecture is the conjectural law of motion is that so now I'll put back a time variable. I'll think of a curve as a function of s and t. And then gamma sub t, the time derivative, should be the velocity we just computed. times 1 over 4 pi log epsilon. And if I wish to, I could write it in terms of rescale time tau, and then it would just be, and then this, or we can, after rescaling the time variable. And let me assume I've rescaled it in such a way as to absorb not only the factor of log 1 over epsilon, and I'm sorry, this is crazy. This is 1 over 4 pi log 1 over epsilon, not 1 over log epsilon. Okay, so okay, so this is the conclusion this leads to. This calculation can be done more carefully, but it can't be done that much more carefully because it's really so what it's doing is assume we have this perfect epsilon vortex filament that we get by taking an ideal vortex filament living on a curve and regularizing it in the most perfect way possible with a symmetric modifier, and then compute the velocity field, and okay, and this is what we get. But if I want to solve Euler equation, the Euler equations, there's no way, I mean, how can I know that at any time I have this perfect filament structure? I mean, I can put in the initial data, but if I wait a millisecond, will it still be there? If I wait, a time square root of epsilon to the, if I wait, how will it persist? How can I know that? That seems hard to prove. And so, one can, I could evaluate the integrals and so on, but still, this is at best a suggestive computation. Nonetheless, this is the conjecture that dates back to around 100 years ago, 115 years ago. This is the conjecture, and it's due to, I'm not sure they called it a conjecture. Or if it was phrased as a, well, I don't know. I actually have the paper, but it's in Italian. This was his PhD thesis. I believe he was a PhD student of Levi-Civita, the famous Italian geometer. And Levi-Civita was interested in this question. No one else was very interested at the time. And so Levi-Civita tried to promote it, and he returned to it later on in his career, but no one seemed to pay much attention. But nonetheless, this is a question with a very old history. And as we've seen, there are videos on YouTube that show this phenomenon. So what's the equation mean? So I want to discuss basic properties of the equation, and this means a review of the geometry of curves and surfaces, or of curves. Okay, so assume I have a curve gamma who is defined on an interval. It may be a closed curve defined via a periodic function or a non-compact curve. Let's assume that gamma sub s is equal to 1 everywhere. So this means I have an arc length parametrization. Then we define, well, okay, say gamma sub s. I'll write this as vector t. This is a unit tangent. In other words, gamma sub s evaluated at the point s is the unit tangent of the curve at the point gamma of s. What else? So if I look at gamma s, the second derivative is a vector. The Euclidean norm of that is called the curvature. And then the unit vector in the same direction is called the normal, and is denoted by n. Of course, this isn't defined at inflection points, at places where the second derivative vanishes. And then the binormal is T cross N. So this is just a definition. Okay, and so all of these quantities are obvious, so all easy to understand. If the curve gamma is a circle, in other words, I have a plane, I take a plane in R3 and I have a circle in that plane. Then it's just two, then we may as well assume it's sitting in the XY plane and it's parameterized by whatever it is, R cosine S over R, or sine S over R, where R is the greatest. And then you can see that the tangent is sort of supposed to be the normal point inward in this case. And then the binormal will be in the plane orthogonal, and I forget which way it goes. And the magnitude of the binormal is 1 over the radius of curvature. Right, so if the radius of curvature is small, the magnitude of the normal, the curvature is 1 over the radius of curvature. So if you have a small circle, then the curvature is big. Okay, and so so all these things are very clear if we have a embedded curve in R3, or sorry, we have an embedded circle. And if I have a general curve, then at each point on the curve, well, there's an oscillating circle, there's a circle that agrees with it to second order. And then all these quantities for the curve gamma at that point on the curve will coincide with the same quantities for the oscillating circle because they have the same second order scalar expansion, and that's all that matters when I compute these quantities. So okay, and note that the normal and that all these things, normal, binormal, the directions are selected by the direction on which we traverse the curve. Okay, and so with this notation, you see, so gamma sub S cross gamma SS. What is that? That's cross. Well, so that's just very naively. That's the unit tangent, and then gamma SS is the curvature kappa times the normal vector. And so this is the unit tangent times kappa, this is kappa times the binormal. Okay, so this vector gamma S cross gamma SS is pointing the binormal direction, and its magnitude is the same as the curvature. Okay, hence this equation. So hence star is sometimes called the binormal curvature flow. This is the name I'll use for it, and I'll abbreviate it BCF. It has other names. The vortex filament equation, or the localized induction approximation. And this refers to the kinds of formal arguments, the local induction approximation, or the sort of formal arguments I did above in deriving the equation in this sort of hand-wavy derivation equation. Okay, so this equation, so what I want to do in the next week or two is to say a bit more about the hypothetical connection of this equation, of this geometric evolution equation, to vortex filaments in Euler, and also in the gross, well, the structure in gross projective is basically the same. Let me first describe some solutions. So, well, for example, if I start with a planar ellipse, then it'll have a certain orientation. The tangent and the normal are both in the plane, and so the binormal will be orthogonal, either up or down. The system is up. Then so it's going to move upward. If it's convex, it'll always a convex shape in a plane will move. Will all move in the same direction up or down. For this ellipse, it's more curved at the ends, and so it'll move more quickly there. It'll start to curve, to bend up like this as it moves, and then who knows what it'll do next. You can see you can see simulations on YouTube if you type vortex flow equation or binormal curvature flow. You can see various simulations. They're interesting simulations involving polygonal curves, and so a curve for which, say, if my initial data is a square sitting in the plane, well, then the curvature is 0 everywhere except at the corners, where it's a delta function. And so the equation doesn't really make sense. Nonetheless, you can put it in a computer. If you have code for simulating the equation, you can put this data in a computer, and it'll work fine. It'll produce reasonable looking pictures. So so that's what's, of course, the basic solution is a circle translating with constant velocity. So then for a circle, this binormal curvature vector is a constant magnitude, and it's pointing in the same direction everywhere in the circle. Another solution of a sort of similar, well, another solution, a short solution is a line that doesn't move. And interpolating between a line and a circle, there are spirals. And so a spiral will move by a combination, or a helix will move by a combination of, well, I mean, I guess it's hard to distinguish from our point of view between a translation in the z direction and rotation, since those look similar, but it moves by a combination of translation and rotation. There are also things that look like if I take a circle and then wrap a helix around it, this thing would move by, it would sort of rotate and translate upward as it goes. So there are things like that. These are known, say, soliton solutions of the equation. Let me see. So there's a remarkable property, and so in order to establish, to say more about the hypothetical, the conjectural connection between the Euler equations and this geometric evolution problem, I'm going to spend some time talking about properties of the geometric evolution problem, the binormal curvature flow. And so properties of the binormal curvature flow. And so the first one I want to talk about is actually not so relevant, as far as I know, to the hypothetical, to the conjectural connection to Euler, but it's interesting. And so this is the so-called Hashimoto transform. This is kind of remarkable. So suppose gamma solves this. And let me define, so let's let kappa, I'll have to give a definition. Well, so it's the curvature, by which I mean tau of S is the torsion. I forget the formula, but here's the definition. So I'm doing this slightly backwards, but consider we have I've told you we have this so these I've defined the tangent, the normal, and the binormal. These are an orthonormal frame for R3 at every point, at every S. They're normal. Okay, and it's a function of S. if I differentiate this, well, what happens? So by definition, the derivative of the tangent is kappa times the normal. Okay, it's also true that if I differentiate this, this matrix here is going to be antisymmetric, because so at every point, if I call this matrix E of S times E transpose of S is the identity. And so if I differentiate that relation, I'll find that E prime of S times E transpose plus E times E transpose prime is 0. And if you look at that, that will tell you that this is antisymmetric. In other words, if I differentiate tau dot, if I differentiate identity t squared is equal to 1, I'll find that t prime dot t is equal to 0. And if I differentiate identity t dot n is equal to 0, I'll find that t prime dot n is minus t dot n prime, which is exactly this antisymmetry relation. Okay, so so I have a minus kappa of S here. This is 0. This is 0. This is 0. And so there's one other non-zero coefficient. And that's by definition the torsion. Okay, and so from this we can say, well, the torsion is if I take n prime and I take the dot product with B, that's what the torsion is. Okay, so I'm describing the remarkable Hashimoto transform. So I have this curve which solves the equation. I look at the curvature and the torsion, and I define a complex valued function, psi of t and s to be e to the, what is it? It's curvature squared. No, sorry, it's curvature times the antiderivative of torsion. Okay, so we define this complex valued function, and then the remarkable fact is that psi solves a nonlinear Schrodinger equation. So a famous PDE, I dt psi is equal to, I have to get the signs right. Okay, let's do it this way. Plus dss psi plus 1/2 psi squared okay, so okay, let me remark here when I carry out this, so note there's a t dependent constant of integration. Right, so whenever I integrate this, as soon as I fix some base point, if I integrate from some S naught of the torsion, then of course this is fixed. But in general, when I compute an antiderivative in the S variable, I'll get a constant integration, and that'll depend on the time I've chosen. And so that gives rise to this which so that gives rise to this. And so if I'm careful, I could choose the constant integration in such a way as to make that a of t equals 0. Or if I'm careful, I can choose it to make it something. If I prefer it to be something else, I can choose that also. Okay, and so let me see. This is kind of remarkable because a lot is known about that equation. Well, first of all, it's more linear. If I look at the binormal curvature flow, this, I'm multiplying derivatives. I'm multiplying first and second derivatives, and that makes it a rather nonlinear equation. Here, the derivatives appear linearly, and the nonlinears involve only the function itself. So it's more linear. And as you may know, this particular equation has these remarkable analytic properties. It's a fully integral equation, so it has infinite conservation laws, and there are these techniques for writing down exact solutions and so on. I would like to sketch the derivation, but I'm not going to. But it's interesting. Anyway, that was discovered by Hashimoto in around 1971 or 72. So this equation. So on some level, this binomial curvature flow this transform can be inverted. So given a curve which solves this binomial curvature flow, I can associate with a composite function who solves the cubic NLS. On the other hand, the curve can be inverted under some reasonable assumptions. The transformation can be inverted. You can construct solutions of the geometric flow from solutions of the NLS. Okay, and what else? And so here's a right. Well, here's some other properties. I like arc length parameterizations, and so note that, so assume gamma solves this binomial curvature flow. Let's look at, so I'm free to insist on an arc length parameterization at time 0, but will that be true at later times? Let's compute that. And so I'll have ddt, I'll have gamma st dot gamma s. And so that's ds of gamma t is using the equation. Okay, and so I get this, the first term is clearly 0, since I'm taking the cross product vector with itself. And then the second term vanishes because gamma s cross gamma ss is orthogonal to gamma s, and so I get 0. Okay, and so if in particular, if I arrange that I have an arc length parameterization at time 0, that will be true at later times. Arc length parameterization is preserved by that equation. And so the integrator tells me also if I have a closed curve, the length will be preserved by the equation. The length doesn't change. Next, I'm about out of time, but if I look at the curvature scored, I can do similar calculations. And what will I have? I'll have Okay, so this, I should have done this beforehand. So I'll get a term involving, okay, so this anyway, we're out of time, so I'll stop here. This should equal 0. But the calculation has a step or two that I've forgotten about. So okay, so we'll resume this discussion tomorrow. And so, so the plan is spend some time discussing properties of the flow. There's one or two that I want to highlight, and then use that to have a slightly better understanding, a slightly less hand-wavy, and in my opinion, slightly more convincing demonstration, or say support for the conjecture that vortex filaments in the Euler equation evolve in some limit or in some situations by this geometric evolution problem. And so that's my goal. And okay, any questions? So sorry, I ran out of. And if there are no questions, I'll stare at this and see you. So again, SST. This is really, this has got to be easy. Oh yeah, this is totally wrong. No, what am I doing? So this is gamma SST cross gamma SST. Okay, so plainly I should have figured out beforehand what I was doing. Anyway, I'll stop this.